I want to make two remarks of a nature, not common mistakes, but clarification or something. We've been a little careless with some words, and I would like to explain that you have to be careful about it. The first time it came up was with this question when we had two sources, A and B, and they have two detectors. And the question is, what do we do with the case when the two photons come from one source? It's not a particularly hard problem. When the two photons come from one source, one goes in one and one goes in the other, and you multiply those two amplitudes and you get a number. But the question is, what do you do with that number compared to the numbers we got when we said that one came from each source? I give another example of the kind of problem, and then we'll explain the situation. Something slightly more familiar. Guess what? Here's a layer of glass. And here's a source. I understand there's some objections. It isn't all to be mellow. After all, some of this thing has to be of some difficulty. After all, it's quantum mechanics. So suppose we have a detector here, the detector, which we studied, but we also have another detector here. Two detectors. And I ask the following question. The event I want is that one or other of the two detectors goes off, right? You might be inclined to calculate that in the following way. The answer, I want one or the other of the detectors to go off. So first I calculate the amplitude that this goes off. Number A detector, and this is B detector. If I ask for the event, and I'm going to put that in quotation marks because it's not quite what, we'll see why. The event is one or other go off, one or other detector goes off. I'm illustrating an error, okay? So when you're taking these notes, put some kind of circles around them. It's in the margin, not quite right. First we calculate the amplitude to go into detector A in the usual way by adding those two things and so forth, which I will not go over again to your delight. And the net result is some arrow, which represents the amplitude to go into detector A, which is the sum of two other arrows from reflection from the two surfaces. Now we start all over again and we compute the same thing for detector B. The reason detector B may be different is at a different distance, let's say, or something like that. It's a somewhat different circumstance. And this, for instance, might be the arrow for detector B. Now I want one or the other of the two detectors to go off. What shall I do?
Square them and add.
Yes, you should square them and add them. But there were those who might think that since this is two ways that the same event can occur, you would add the arrows first and then square it. Yes, it's not the same event. And so by event, we have to make a definition to decide what we mean. How do we know that this is the two events and not one event or something? The answer is this. After this experiment is finished, you could determine which of the two of these went off without any further disturbance to the system. In other words, you simply didn't pay enough attention to as much, you haven't defined the process that you're talking about in as much detail as you could have defined it without changing the circumstances. In other words, this detector goes off and it leaves its thing shaking and wiggling and everything else, and it's ringing and it's gone off. Or this could have gone off. 20 minutes later we can come back and discover which one it was. On the other side, you see, when we have only one detector and we were adding those two amplitudes and we finally got the photon here, there's no way that we can run back and look and see which of these two surfaces the thing reflected from. It's an event, incomplete, it's finished, and there's no way to tell which way it happened. In principle, there's no way. Of course, if we refuse to look at these, you'd say, then there's no way to tell. But there would have been in principle, and so to speak, nature knows which one went off, even though you don't give a damn. You understand what I mean? Here, there's no way if you gave a damn that you could find out in the way I set up the experiment, okay? So what happens in that is that you have to consider this as really two different events, each one of which has its amplitude and its probability, and all we take is a probability of two different things, and we add them in the normal way of adding probabilities. So for this example, this gentleman guessed correctly that we square A is the probability for A that A goes off, which is just a conventional answer that you'd expect before you learned anything about quantum mechanics, that B goes off. Okay, there's a little bit of subtlety in an exact definition of what a pure event is, a simple event, but after a little practice it for use, you get to know, all right? But I just want to point out that particular possibility. Now, what happens in this case is with this case of the A and B emitters, it's possible to come back later and look and to see which one, if you had checked what the energies were before, and afterwards check which ones have lost energy. Therefore, whether both photons had come out of A or each had come out of B. Even though you looked at these detectors in principle, you could have told from which source, whether they both came from the same source or they came from two different sources. Whether, for instance, this lost any energy. If it didn't, nothing came out of it. So therefore, afterwards, you could determine. So this is one of these things that we have to do. This case, on top of the other, and add the probabilities. By the other, I mean the case where we assumed that it was 1 and 1. We did the 1 and 1 correctly. There were two ways it could happen. On top of that, there's a completely different event that they both come from the same source, because that could be distinguished even afterwards. It isn't intractably inseparable, okay? Okay? What? There's a little problem there, yes. You should have some mild problem with that. That's perfectly natural. I mean, in getting the full definition of the separate event, where's the problem?
I saw a problem how you said you considered separate them afterwards. I don't.
Well, if you had been careful to prepare these things, which are the atoms which are going to emit the photons, okay, ahead of time, so you knew all the conditions, and then start the experiment, and then get these counts here, you could, in principle, go back and look at these atoms and find out from which box the photons have come, whether A or B, to see whether some of these atoms have changed their condition. Okay?
Oh,
and if that's possible, then there's no more interference between that new possibility. If you could tell the difference afterwards, okay?
Can you do that with a laser?
Well, if you had measured the positions, if you had measured these atoms carefully enough ahead of time and looked at them later, you could just simply tell because they lost some energy. Yes?
Presumably this in principle also includes situations which practically we couldn't do it, like if these were stars.
Yes, practical has nothing to do with it. So nature knows, but we can't do it. That's right.
We still have to add in these.
Yes, and so that's a little bit subtle, and one has to get to learn what are fundamental processes and what are not. Actually, with a little practice, you pretty soon get the idea interference when it's all finished and you can't tell. Let me give a counter example for fun. Suppose that these two surfaces, although they were really glass to air, well, let's say there were two layers here. I had double glass things, and so I had 4 amplitudes to add the usual way and so on. You'd think everything is right, you should add 4 amplitudes, and you're right. But if this thing were free and movable, then when the photon bounced, it would leave this with some momentum, or this with some momentum. It would tell which one it was that did the scattering. And therefore, we have a situation so arranged that we could measure the momentum of them separately to determine which one did whether this layer or this one, this pair of layers, or this one scattered the photon. If it was possible afterwards by looking at the speeds of these things or something like that, then we'd lose the interference that we would have had. I'll give another example of that kind of loss, perhaps when we talk about some other things. It is possible to arrange circumstances to find out, to set it up so you could tell which way it went, and when that happens, you lose the interference. That's an example of the uncertainty principle. If you could measure which one of these things did the scattering, then you won't find the same result in the experiment as if you couldn't. You can't if these were locked together, frozen with bolts, because then you can't tell which one is moving afterwards because they were locked together. So the correct way that this experiment really has to be done to make it work very well is that these are locked together with bolts out here so that they're not free, that I could measure their momentum. Or that the momentum was very high or low and I can't measure it for other reasons, but that's okay.
Basically what you're saying, you lock together is that the whole entity. So
The whole entity is together, so that the distances are all relatively fixed and they're not movable and all kinds of stuff. Anyhow, that's one type of situation that you have to be just to a bit careful of. It looks frightening now because you can make mistakes, but it's very hard for me to define precisely how to avoid mistakes in every case in an elementary way. Yes?
It seems to me what you're saying is you have to not only have two separate layers, but you need to have a mechanism there capable.
That's right. It has to be of such a way that it could, in principle, be determined afterwards. I don't mean you actually are able, just like the guy with the stars, he can't go up there, but that's only a practical problem. Suppose we went up there, then we'd be in pickles. Suppose we, yes, okay. That you can't conceive of measuring it. That also illustrates another very interesting thing. Suppose there were photons of two different kinds, and as a matter of fact there are. They're called polarization X and polarization Y. But suppose there were of two different kinds. And suppose that, and we could distinguish them, that is possible by putting Polaroid in front of the detectors to make one that detects only X or only Y. Now, if we had two different kinds of photons, X and Y, and let's suppose we know that one of them emits an X, this one emits an X type, and that emits a Y type. If that happened in that case. See, I didn't deal with polarization, but I'll show you what happens when you do. Then we thought we were going to have two amplitudes, right? We remember we talked about this photon might have gone to this counter, and this photon to this counter, or this photon could have been the one that went to this counter, and the other photon would have been the one that went to that counter. But it was possible in principle to determine what the polarization of this photon was that came in. And if it's X, you know it didn't come from that one. So these two cases no longer added. That was a mistake. I said you add the amplitude for the two cases. It is true only if the polarizations are the same, if the photons are indistinguishable. Okay? Actually, it's possible to have two different kinds of photons, and then if there are two different kinds of photons, you don't, and one happens to emit one kind and the other kind. That case shows no interference because the thing you're asking is more complete. Does this receive an X photon and that one a Y? That's one event. Another event is this receives a Y photon and that receives an X. One of these two events is done only by the blue lines, and the other is done only by the orange lines, and you have to add the probabilities for those, not the amplitudes first, when they're two different photons. No, yes, it would if there were always two different photons. But since sometimes they're both the same photon, the diffraction effect is again there, okay? It's made it smaller, relatively, by that. However, the antennas of the receivers that are used, or the photomultipliers, are always made so they're only sensitive to one kind of polarization and the same kind. In fact, if you insisted on putting two detectors, let's say radio receivers, one with its antenna pointing one way and one with the antenna pointing at right angles, it turns out that that's a way of distinguishing the two kinds of photon. Then only one would only be able to receive the X and only the Y, and they can't get mixed up anymore, okay? So, but that's not the way it was done, and in fact we're disregarding polarization, so what I said was right. In other words, if you have no way to tell which photon was which, and all photons look the same, then there's interference. You have to add the amplitudes. When you can't tell, even in principle, then you add the amplitudes. That also shows a very curious thing, that photons are absolutely identical. We can tell what we mean by absolutely identical. No one is going to come along, aside from this polarization business, say aside from that, and be able to distinguish photons. Because if he could, we wouldn't have found interference in detectors like this. But we did, therefore photons must be identical. There never will be a new way to distinguish them, because if there were, we would be able to obviate the interference, but we measured it's there, therefore they're identical. That's a very, very interesting aspect of quantum mechanics, and there are many such things. There are many wondrous things, such as this, that you can tell that two particles are fundamentally and absolutely forever indistinguishable, therefore identical, just by noticing there's interference between cases. And that can't be done in classical mechanics. In classical mechanics, say, well, they look very close, but maybe if I measured more accurately, I'd see there was a millionth of a gram difference in the weight or something. But in quantum mechanics, you can define identical.
If you have two differently polarized sources,
Yes.
and you have detectors which are unsensitive to that.
Yes, but you see, they could have been sensitive. That is, you didn't bother to look at as much detail as you want. It's just like having the detector there two detectors and you say, well, make the hole bigger, you go into either one, but you should have to separate.
If you have that situation,
Yeah.
which do you get? A diffraction is...
No, if you can't, if your detector in actuality is not built so it is able to detect, it could have been built that way, but it wasn't, then you add as if it was able, okay? You take the cases and add them together.
So it would be the,
Squares added,
okay.
yes. Squares added, yes.
But,
Well, it's like having two detectors, and it's the same as one big detector with a big hole. We could do it better, we could do it finer. We should be able to say the amplitude to come to this point or this point and this point separately and not interfere them. It's a little complicated. It depends on how the detectors are built. Okay, turns out it sounds harder than it is, okay? In practice, it isn't very difficult to tell when you do each one. The places where it's surprising is that the idea of identical particles. When two helium atoms, for example, are identical in every way, they don't have polarization. And when you have an experiment like that's where you have helium atoms emitted and received, you'll find interferences. And so, but if you change the helium from helium-4 to helium-3, a different nucleus, so that you could have told the difference, you lose the interferences. And that appears in the strange properties of liquid helium, which is especially strange because all the atoms are identical, and you get a lot of effects because one can replace the other, and you get lots of interferences, and it makes liquid helium have strange properties different than any other liquid. It flows without resistance, and it has all kinds of zero, well, it conducts heat perfectly, and it does all kinds of marvelous things, all quantum mechanically understandable, but all based on the fact that all the atoms are identical. If you put some of a different mass atom in, which ordinarily in chemistry has hardly any effect, it's the same atom, but just a slightly different mass, then that one of different mass simply separates out as a separate liquid. They're two things that are just independent. Because one works only because all the atoms are identical and these ones don't fit in and they get pushed out, right? Different energy and so on. So identity is something easily identifiable, definable in quantum mechanics, exact identity, where you can't do that in classical theory. So those were one of the two pitfalls. Yeah, it is kind of marvelous. That is one of the things I have to remark on. I didn't mean to remark on the identity, but I noticed it in passing. The other is, because some of you, I've been drawing lots of arrows. There's one little situation where I've been drawing a lot of arrows and I had to explain what they are. It's when I change the problem. For example, I could, with the source here and some kind of reflectors and whatever, any problem, have told you there's certain sources and so on, told you the amplitude to find a photon there and worked out an arrow for it. But had my detector been here, I would have worked out a different arrow for it from the same origin. Right? Well, there's no particular connection to those arrows. They shouldn't be added or anything. They're just for two different problems. And so sometimes you see me draw a lot of different arrows for different thicknesses or for different circumstances. And they're not the kind that you multiply or add or anything. They're just different arrows, belong to different events or different problems. It's straightforward. However, although it is straightforward, it's common in physics to describe all the arrows for the amplitude for a photon to arrive in all different places in space, all over. And so then you get an arrow that depends upon location. That's called a function. The arrow is a function of location, or the amplitude is a function of position in that case. And that function is called the wave function sometimes. So I just wanted to mention what the wave function is. For a photon, it's the amplitude to find a photon at a position. But given for every position you might want to ask about, sort of as a list ahead of time. But we didn't do much of that, and you were not likely to get into that question. Okay, and that's the two little minor. One was major and the other was minor. Yes?
The question is technical.
Yes, technical, good.
In the wave picture, field picture for the Hamburg-Brown twist interference, it's really cute even in that mode. Basically, what you're doing is correlating the intensity fluctuations.
Yes.
And in the argument you just gave, would that in that picture be saying that the intensity fluctuations for each polarization were the
Yes. Yes. That's right. If you want to do it that way, yes. The technical question has been answered. Next question. That was a fly, not a black dot. Okay, to remind you then, let me just remind you without writing it all down. You probably have heard it so many times that you begin to believe it. We're going to calculate probabilities of events. We had a little nerve-wracking moment here where we had a little problem defining events. We calculate the probabilities of events by having every probability of a completely defined event, one of these perfect events, by computing the square of an amplitude. And an amplitude is a complex number or an arrow on a piece of paper. And the arrows are to be calculated by composition, by a couple of sets of rules. The first is that when things can happen in more than one alternative way, the total amplitude is the sum of the amplitude for each individual way. If a particular way can be analyzed as a succession of events or the concomitant action of more than one event, like two particles, then we multiply the amplitudes. I have defined what I meant by add and multiply arrows, and I don't think I have to review that. All right? To those who know complex numbers, there's a nifty way of describing arrows, but I won't bother with it, I guess. And that the multiplication and adding then is a simple algebraic process, rather than drawing all this stuff up. But that's just a technical point, which you may discover somewhere when you read about complex numbers, and we'll let you guess how it gets put together later. Now, with that, we have then been able, therefore, to take a complex process and divide it up in parts. First, by considering that there are maybe many ways in which a thing can happen, and we just have to sum the amplitude for each way. Then when we look at any particular way, we've divided that into a sequence of pieces that happen in succession or concomitantly. And those amplitudes for those have to be multiplied. And we mentioned last time that therefore, well, we see therefore that complicated things can be reduced to simpler ones. And the question is, how many elementary ones do we need as sort of a minimal basket out of which everything can be built? And that is what modern physics is about, so to speak, trying to find out what that minimal basket is. Another way to put it is that in these laws of quantum mechanics, which I've stated generally about summing amplitude, making amplitudes, summing amplitudes, and multiplying amplitudes, I've set out a method or a stage, a new framework, a new kind of way that the laws of physics are going to be described. Now I'm going to tell you the amplitude for this and that fundamental process, a simple part. What simple parts are there? It's like setting a stage and saying there's going to be a performance on this stage which is limited in certain ways and behaves in certain ways, but I haven't told you the performance. In other words, we have the rules of quantum mechanics which tells us how to handle amplitudes for different kinds of things to happen, but what kinds of things can happen? All right? That we have to add. And that's not completely known. That's always the research of physics is trying to find what the fundamental processes are. Sometimes it is said we are trying to find the fundamental particles or the fundamental interactions. It's the same thing. What we're trying to find are the fundamental events, the simplest possible things out of which we can make all the more apparently complicated ones. Right? Now, for a great deal of nature, and all the nature that was known to people up to 1930, well, not quite, because they had discovered radioactivity by that time, but for a large part of nature, and I'll define it better if you want, everything can be understood by the following parts, that there are electrons, and I'll translate all that into quantum mechanical language in terms of amplitudes in a minute. There are electrons, and there are photons. That takes care of all kinds of electrical effects and things like that. In addition, there were the nuclei of atoms. The nuclei of atoms were rather complicated, but in most experiments that don't involve nuclear excitations or nuclear reactions, we don't have to know much about it. We can think of the nucleus, although it turns out now to be understood as a complicated thing, as just a little ball, a special particle of its own. So what I want to, but the electron and the photon have turned out up till now not to have parts and not to be explained in terms of something else, whereas the nucleus is now understood in terms of a more complex thing. So if we go back, we just imagine I'm going to tell you the rules for electrons and for photons, and very crudely for a nucleus, but that's not really what happens in a nucleus because it's much more complicated inside. Okay? Most important ones are the ones for the electron and the photon, because those are going to be exact. The one for the nucleus is only approximate. If the nucleus doesn't come apart or it doesn't get excited, it's a rough approximation. It may be possible in the amount of time that we have to give a rough outline of where we actually stand, sort of. I mean, how many parts we found the nucleons need and all this other stuff. But let's, it's really remarkable how many phenomena are understandable just from photons and electrons. As we mentioned, photons are X-rays, photons are radio waves, photons are electric fields in the end, and photons are all kinds, are the origin of all kinds, all the electrical and magnetic effects that you have. And electrons are the mobile little parts of atoms, and they can move at different speeds, or have different energies, I should say, more correctly. There also turns out to be another particle which is very closely related to the electron, which I'll come to as we discuss this. So, if I'm only dealing with electrons and photons and I'm not involved in a nucleus, these are the rules. If I'm added that I have to be involved in a nucleus, I have to add more rules. In fact, I have to add 92 more rules, or how many nuclei there are, actually hundreds. 100 more rules for each nucleus. All these 100 will be made into a few when we understand the guts of the nucleus, which we today, I think, do, all right? In which case we can make the rules simpler. But at the present time, the simple ones are for the electron and the photon. Nothing, there has no parts, we don't know any way to make it simpler. The nuclei is an approximation if they're not excited. Then it looks simple, but that's not right because they could get excited. The nuclei I'm cheating on, I'm shortcutting, but the other ones are exact as far as we know today. So, I'm leaving out gravity, and I'm leaving out what's called the weak interactions, and neutrinos, and mu mesons, and a lot of other stuff. I'm back in the 30s. And the sort of vast amass of phenomena that I'm going to be having to deal with. The burning of gasoline in an automobile engine, the electric generator at Hoover Dam, the crystallization of salt, what determines the color of copper, and the human body and all of life, if the life is reducible to biochemistry, to chemistry, and to physics. Therefore, I mean, one is the basis of the other. So it's a big, big thing. So, okay, you'll be satisfied. It has to do with the lights, everything you're seeing right now, as a matter of fact. Okay, now the parts, the fundamental operations when we have only electrons and photons is that we have two particles, one we call a photon, and the other, which includes light, X-rays, and so forth, and the other we call the electron. And if that was all there was to it, we need one more thing, that's called the interaction between them. There are three rules. How a photon goes from one place in time to another, how an electron goes from one place in time to another, and how they couple to each other. All will be explained. Right? So first, up till now, I haven't been dealing very satisfactorily with the time, which has been pointed out to us several times by Professor Dr. Lilly. And now, at last, I am going to do it right. I am going to deal with time and space together. And so we're going to ask a little more detailed question. What is the amplitude that a photon emitted from one point in a certain place in space appears or gets to another point somewhere else in space at a different time? Let's suppose this is emitted at a certain time at a certain place, and that this goes to another place at another time, all right? It may not be familiar to you to make a plot a diagram, let's suppose that the space was only one-dimensional. Then we could use this direction for time. For example, let's suppose that objects that we're talking about can only lie on this line. And I want to know whether a photon liberated at this point, at a given moment, can arrive at this point at some other moment. Then what's very convenient is to plot the moments vertically. That is a measure of the time in the diagram. So if I mean this point not at 0 time, but say 2 moments later, say this is 2 moments. You figure out what a moment is. It's a nanosecond for you, a picosecond. No. That would be represented by this point here, not this one. And this, where I'm talking about receiving the photon, would be represented at this horizontal position. Well, let's call it X, the horizontal position, but at a later time. It's a kind of funny graph because most people plot time horizontally. I love to plot it vertically. All right? Such a plot in which the space is horizontal and the time vertical at right angles to it is called a space-time plot. Of course, the actual space is 3-dimensional. So all I have to do is erect an axis at right angles to all the directions that we know in order to represent the time. That's an imaginary representation. It's a 4-dimensional space, really, space-time. So what I need to do is to tell you what is the amplitude that a photon liberated from here gets to here. And there's a formula for that. And it depends on this position and this time and that time. This position I will call something like x1. Actually, because there's I put 3 letters down, because really to locate something in space I need 3 numbers. How far from that wall, how far from that wall, and how far from the floor. You're probably familiar with all this. If you aren't, you'll understand the spirit of it, but not much of the detail that I'm trying to give, okay? And this would be located at some other place, we'll call x2, y2, z2, and at another time t2. This is a time t1. And what I have then is simply a formula. The amplitude for a photon to go from here to here is an arrow, which depends on all these numbers. And I'm going to give you a formula to tell you what kind of arrow, how you put the arrow for the different distances. Well, I should like to be able to do that, but I'm not actually going to do it because the formula is a little bit complicated, very mildly complicated. For those who know enough mathematics, I'll write it down, but that will only make the others shake, and I don't want.
Okay, I like to be shaken.
Okay. As you might guess, this arrow that I'm going to make is only going to depend upon the relation of these two. How much time the delay has been. It's only going to depend on T2 minus T1, the difference in time. And it's only going to depend upon the difference in this position. Which would be the separations in the 3 directions. Right? So it's going to depend only on those differences. That's not 8 numbers, but only 4. It makes it easier. But if you know anything about space, you realize it's not going to depend only on it's only going to depend on the real physical distance between the 2 points, not the difference in this coordinate and the difference in this coordinate and the difference in that coordinate, but only the distance. And the distance is the sum of the squares of the 3. If it was only 2-dimensional, you all know that. If you have 2 points in a 2-dimensional world, the distance squared from here to here is the sum of the squares of this and that. 3 dimensions works the same way. So it's the sum of these squares that represents the distance squared, which is the only combination that comes in. So I know it depends on the time difference, and it also depends on these sum of those 3 squares. You want to take a square root, you can. We don't have to bother. When I say it depends on something, it depends on the square as well as the thing. That's the distance squared between the points. So as a matter of fact, you see it only depends on 2 numbers. Now, the theory of relativity was a study of the relations of time and space, in which we've learned that the laws of physics are very remarkable. They not only don't depend on anything but distance, but there's a combination of time and distance as the only thing that they can depend on. And that is, as you might, if you're happy with 4 dimensions, 3 dimensions, add another square. Why not? So you do that. Wait a minute, that was wrong. It should have been a plus sign, and what is that C doing there? All right? I'll explain both. I won't explain one, but I'll explain the other. The C is easy. It's because time is measured in seconds and distance is measured in centimeters, and that was a mistake of whoever it is that invented centimeters and seconds. It would be as if we were trying to measure distances in the sea, and we were naval experts, right? And we have a very, here's the water, right? And when we measure distances between ships, we measure them in nautical miles. And when we measure the distance down in the sea, we measure them in fathoms. So we have a different unit that we're using for the vertical than we for the horizontal. It will be not correct to add this distance square. If you want to know how far it is from here to here, it's not correct to add that distance in nautical miles squared to this distance in fathoms squared. Before you want to use your nautical mile distance, you've got to correct it by multiplying by a number, which is, of course, the number of nautical miles that's equivalent to a fathom. Okay, so we need a number here, which is the number, a fundamental unit in physics, which is the connection between space and time, and tells us how much distance in this world of space-time is equivalent to a centimeter. And this is in centimeters per second. It's like nautical miles per fathom is what we would have to multiply. The reason it's squared there is more correctly, it would be easy to understand. I first have to fix up the time and then square it. And it's either I could square, well, it's this, I should have written it like that. So let us say for a moment that we have fixed up this unit. We're not like the guys, the engineers or the naval architects or whatever they are, naval people. We don't use fathoms and nautical miles. We found out about that. We use the same unit. So if you imagine I use centimeters of time. A centimeter of time is the time it takes light to go 1 centimeter. That's a unit of time. And that unit, then I don't need to see it all. And now the beauty of the formula becomes more apparent. The only magical thing is oh, I made the minus sign in the wrong place. Minus that plus these. Why the time has the opposite sign of the space, nobody knows, but that's the way we find the world. It's a very beautiful thing, an extension of Pythagoras, which said to add these squares. We also add the time square, except we subtract. That's the fun of physics. It's always got nature, I mean. It's always got one of these lovely flick-flacks inside, and all the marvelous consequences that come from the sign being reversed, which makes time appear entirely different than space to us, and has all kinds of consequences, which is nothing but a change in sign in a formula. If it were plus, the time would look just like space, but in a new direction. It's actually minus, so it feels entirely different. The discovery that nature always uses that combination as the fundamental quantity was the discovery of the special theory of relativity. I am assuming that then. Now we have only one number, which is sometimes called the relativistic distance, or the relativistic, yes, between these 2 points. It's sometimes called S squared, the square of the relativistic distance between those 2 points. That's very bad to call it S squared, because it sometimes could be negative. If the time difference is bigger than the space difference, it's negative. The space difference, so they have to say it's S squared. It's time-like separation or space-like separation, depending on the sign, all kinds of garbage. Never mind, whatever, this is what I mean by it, whatever I call it. I'll call it the interval between 1 and 2, all right? Anything. The answer only depends on that interval. How it depends on the interval is, unfortunately, a little bit complicated. I'll tell you what it is exactly for just one moment, and then I won't say any more. The arrow for a particular interval is generally in the, almost always, in the horizontal direction. I say almost always, and I'll explain. The length of it is proportional to 1 over this. The further, the bigger this interval is, the smaller the amplitude. When the interval is 0, it looks like this is infinity, because it's 1 over 0. It is really, I haven't normalized these right. We can't have amplitudes bigger than 1, but when you integrate over this and that, I mean, when you add together different cases, it all comes out all right. Let's not worry about a normalization to get the units 1. It's 1 over this distance, and it's therefore very, very large, and most important only when this square here matches this. That corresponds to saying that the time difference is equal to the distance, which is the way light goes when we're studying light. That's why light goes that way.
Repeat that? Repeat that.
This is biggest amplitude. In fact, it's practically infinite. When this square equals this square, the sum of these. This distance is the distance squared. So it says that when the time interval is equal to the separation in distance, just a moment, the light, that's when we get the biggest amplitude for going. That condition is the condition that light goes from one point to the other, because the speed of light has been used in this comparison. So I've come to the remarkable conclusion that the amplitude is largest for a photon to go from one point to another when the circumstances are that light can go from one to the other. At the speed of light, right? But the same thing, because we're studying light. And I made the remark, of course, we're studying light, so it's natural that... Actually, that's why light is used as the velocity of light is used as the scale. The number, 2.9977, whatever it is, centimeters per second, is a very fundamental number. That light goes at that speed is a property of light. That number is really the scale difference between fathoms and nautical miles, and is much more fundamental than... There may not have been any light, and nothing would go exactly at that speed, okay? Then we'd have nothing that went at that speed. We could still have discovered that number and be using it to convert our times into spaces to make our formulas easy. It happens, though, that light goes at that speed because the answer 1 over this thing, which is the true amplitude, is so big at that point. I must also say that there's another component to this. Most of the time, in fact, when this is not zero, the arrow is this way. But when it's near zero, not only is it infinite this way, but there's a big infinite component in that direction. In other words, the arrow suddenly flips over and changes direction. It's a complicated little thing. It's called the delta function, if you've ever heard of it, but I don't want to bother you with it, okay?
Question.
Yes.
What do you call it? Amplitude? Is it 1 over which component? Is it over the whole thing, or the one component?
No, 1 over the whole damn thing is the answer
Okay.
for the amplitude. What happens is this, what I want to say is this, to be just a little bit more, just a little bit, it isn't going to help you any, but I just want to say something. If this number, the distance, is bigger than the time, it's more further spaced than there's enough time to go, let's say this is plus. 1 over it is plus. This is plus. But suppose it's minus, that means there's a little bit too much time and not enough space. Then the answer is minus. So it jumps, you see, from this direction to this direction. Right as you go through the zero, right as you go through the right place where light usually goes in the old-fashioned classical way. So you would think it just flew back across here, but it doesn't. It flies by going around a circle. In other words, it gets larger and larger this way, and goes zing, and it shrinks. And the zinging and shrinking is infinitely fast as you go right past that point, okay? That's a complete, correct description, but it's not very useful for you. At any rate, we do have the formula for how a photon gets from one place to the other, and it's a function that it depends on. It means it depends on. That's what a function means. And I'll write P for the photon depends on the first point and the second point's location, numbers to locate it, okay? The way it depends on it is only through the interval. I've described it a little bit, right? And it's biggest when we have the conventional circumstance that light could get from one point to the other. Well, we already discovered something horrible. A photon can go at places...
The separation between the 2 points that a photon can reach is always 0.
No, it's not always 0. There's some amplitude to go to places where it's not 0. The biggest amplitude is where it's 0. And you usually have this game of interferences and games with the arrows adding up and canceling out. So in practice, it looks as if the photons can only go exactly at the speed of light. But it's not true. There is an amplitude to get to places where they don't belong, so to speak. From the conventional view, they go at the speed of light. It's the perpetual business. There's always some amplitude to go to places like off the 40th part of the mirror where you don't see anything in practice. But it's there. And there is an amplitude to go across places where it doesn't go at the speed of light, okay? Not much amplitude, but it's there.
Does this imply that there's an amplitude for them to go faster than the speed?
Yes. Yes. Actually, though, it turns out that causality is in no way destroyed, because when you go to calculate the probabilities of events that happen before where a photon is supposed to arrive before. When you add all the cases together, always cancel out.
You were the first one to figure that out.
No, not at all. No, not at all. I was the first one to doubt that it was always true.
They always cancel out.
Yeah, but it turned, when we were struggling to find new laws, when we had new particles and strange phenomena, you always go back and try to find out what assumptions you've been making all this time that are preventing you from guessing at the new pattern. And one of the things was that, and I tried to make a quantum mechanics which permitted this to not cancel out, and just got in a knot. I got all kinds of trouble, and didn't solve any problem with it, and was an unsuccessful attempt at resolving mysteries, okay? So it still is true that it cancels out. An attempt to make it not cancel out didn't work. It didn't help anybody. All right, that's for a photon. In the same way, by the way, you'll notice something interesting, that this formula has no natural scale. It doesn't, well, never mind what that means. Now we start again with the electron. Here we get a different formula for the propagation to go from one point to another. That's an amplitude, an arrow formula for the electron to go from 1 to 2. The formula for electron is much more complicated. The arrow turns and does other things, and it's more complicated depending on the distance. It is also only a function, only depends upon this distance, but it's not simply 1 over this distance. It's a more complicated function. It's called a Bessel function of this distance, which I don't bother to work out. However, this particular function actually contains a number in it. There's a certain particular distance that's important, or a certain particular time interval, a certain size interval that's more important than another. Here they're sort of all proportional. You just move it and that thing just gets larger and smaller. But there the function changes its character at a certain scale, which is called the reciprocal scale. It's called the mass. In other words, this thing, E, is a special function of 1 and 2 that depends, that the actual function depends on a number that you stick into it, which we call the mass of an electron. It's actually more technically called the rest mass of the electron. The rest mass of a photon is 0. So this special formula, when m is put 0, is in fact p. P is equal to f of 1 and 2 and 0. The formula we're going to use for nuclei, in fact, the formula for every particle known to man, which includes gluons and quarks and all these other things, are always the same function, but with different values for the n. So it's rather unified, the world, okay? Just different, and the different m's correspond to different scales of the function, different scales. I don't think it helps us any to see these formulas, because what we are at the level of lack of technical calculation ability, we don't need to know what they are, because we're not going to actually calculate them. Finally, so that gives us amplitude for electrons to go from one place to the other, for photons to go from one place to the other. And the last thing we have to do is talk about the connection or interaction between electrons and photons. These are 2 amplitudes. These are formulas for arrow sizes that depend on the positions that you want the thing to go to in space and time. All right? Any questions so far? You got that all right? Ah. You haven't gotten yourself confused. I have confused you. Yes?
You're saying that, which I understand, that the amplitude is significant only when...
For light, yes.
When the space part equals the time part.
If the distances are reasonable. When you're talking about very short distances, one is as significant as the other. It gets more complicated. Yes, but long distances, things cancel out except along the place where this is nearly 0.
I've lost my feel for that arrow rotation. Because you said that...
Well, that old arrow that rotated nice as you went along with time, that one you lost your feel for? You should. Because that one was not dealing correctly in detail with time. I said I had a monochromatic source, and I had to explain what a monochromatic source is, where does it come from, and all that. Everything has to be explained, see, all these things, and I will explain that. You are perfectly right. You are confused. I have done it. It's not your fault. You should be confused. I'll come back and explain that. I'm going to come back. What I'm going to do is explain these principles, and then come back and deal with a few examples, the boring example of the glass plate, and show how the glass plate produces those amplitudes which we used, but now seen in a deeper theoretical sense with a more complete description. It won't look the same, but the answer's the same. And I'll explain everything. You'll be mad because I taught you one way to think, and now I'm teaching you another way to think. This is a more fundamental one, okay? And is the right one. The other was a shortcut to get used to the rules. The rules that I mean are the general ones about summing amplitudes and multiplying them. But the rules for the glass and stuff, that stuff you shouldn't have gotten too used to because I'm going to change that. Yes?
Would it confuse us too much for you to tell us, that there were no natural units? It's kind of some little interesting point.
Yes, it has to do with this. If you change the scale of all lengths and times by using a different unit, the I just changes by a scale, and the amplitudes just change by a scale. And in fact, the way these are defined, by the time you've added them for different volumes and so on, all that scaling disappears. But in the case of an electron, there's another scale. That is, the nature of this formula shifts depending on whether this is big or small compared to an absolute scale of a certain number of centimeters, 3.6 times 10 to the minus 11. When this distance is in this interval is less than 3.6 times 10 to the minus 11 centimeters, this squared, the formula looks mathematically different. It's the same formula, but it depends on that number. Whereas another object would use a different length. That would be another scale at which it would be. It's all in proportion. The different ones correspond to the same thing, but little ones and big ones are hard to explain very well. Functions of scale. Anyway, another way is it depends on the 2 points and on a number that we have to put in called the mass.
You're saying the mass is what determines that scale?
Yes. Yes. Again, there's a shifting of units. I have to presume that c is 1, the speed of light, and also something called Planck's constant is 1, which is another scale. So that this is not in grams, but in a special unit of mass so that it doesn't depend on, it's converted to distances. So I can keep everything in distances. All right? I'm getting to the essentials, and it means a certain amount of cutting around. Now, so we have, these are the relatively complicated formula for the arrows. The interaction is particularly simple. The rule for the, particularly simple in a certain respect. The rule for the interaction is that the arrow is just a certain number, c. And I'll tell you what I mean by the rules for the interaction in just a moment. This value of c is, as far as I can remember, something like 0.3168, bump, bump. Well, that's not exact. No, that isn't right. It's more like 0.1 something. No, 0.098 sec 134, whatever. It's been measured at 8 figures. Why is it that number? Where does that damn number come from? It means it's simply that it's an arrow of a certain size, always the same size, bing. It's one of the greatest mysteries of theoretical physics, that number. Very mysterious. The square of the length of this arrow is about 1/100th, a little bit less than 1/100th. And you may have heard of this number, so I'll mention it. The square of this, the length of that square, is a number which is often written as 1 over something, just for historical reasons. And that number is called 137.03600 approximately, 60 something. It's probably closer nowadays, measured to 590 or 588 or whatever. I think it's known to more figures, but I didn't expect to go this far in my lectures, and I didn't bring the notes which have the numbers. I don't remember them, and
That's the Eddington number.
Yes, it's Eddington's number or the fine structure constant, or it's one of the fundamental numbers in electrodynamics.
Any explanation for that?
No, sir. It's one of the biggest mysteries.
But it was predicted philosophically.
No. No.
Eddington predicted.
Yeah, but he predicted it wrong, huh? He predicted it was 137, which it isn't. And he didn't predict it. Actually, he predicted it was, he explained that it was, he predicted it in philosophy. He had a philosophy in which he claimed he was deducing all this. And he deduced that it was 136, when the measurements indicated it was close to 136. Then more accurate measurements showed it was much closer to 137. And he found a mistake in his philosophical reasoning and discovered that it had to be exactly 137. Eddington. He died before He got worried about the extra decimal places. It's true, but it's not physics, it's false. Okay, so we're not dealing with that. Okay? No, it's not even philosophy. I mean, it just isn't true. It's kind of a numerology. We don't know why that number comes from and have no way to derive it at the present time. This makes it interesting. But let me tell you what it's the number for, and I just have to tell you about this interaction. It works like this. I did already say last time, I gave an example of a problem and showed you what an interaction was, and I'll do it again. If an electron wants to go, let's suppose we have a problem where an electron starts here, it's an electron. Now I'm going to use colors. Good. Photons will be blue, electrons will be black because of that. So hereafter, all the electrons that are moving around in this game are black and the photons are blue. And the typical idea is that an electron can go from one place to another and then go from that place to another and so forth. That at a particular place, a photon always is emitted by an electron or absorbed by some other electron, or maybe it goes on forever out of the system to be absorbed on the moon, perhaps. Let's say we would like to have a photon absorbed here at that moment, at that point. And we had an electron that started here, and we want it to end here. So the electron goes from this particular place in space and time to this particular place in space and time, and the photon is supposed to arrive here. One way it can happen is that the electron goes from this point, which I might call point 1, to some other point where I might call point 4, and finally arrives at point 2. Whereas the photon goes from 4 to point 3. So this would be the typical amplitude. I would draw a picture like this, and I'll tell you how to calculate it. Let's suppose I wanted to calculate the amplitude. Then an electron goes 1 to 3, 1 to 2, and the photon appears at 3. One way this can happen is one way, only one way, is that it goes this particular way, and I'll call that via 4. And you'll see what that means in just a minute. It means the electron goes from 1 to 2 via going through point 4. And the photon appears at 3 coming out of 4. Then the amplitude for this process is the following number, arrow. Arrow. It's the following. I'll write it all down and you see if you can understand it. The product. Remember how we multiply arrows? We multiply the arrows. These represent arrows. The arrow corresponding to an electron going from 1 to 4, which for some reason, I seem to have written these backwards. No, I know. I discovered from experience that to do it the way physicists write it is unnecessary for beginners. It's only a convention, so let's do it the way it looks common sense. We go from 1 to 4. Then the electron goes from 4 to 2. And the photon goes from 4 to 2, 4 to 3. Okay? And there was an interaction. Let's make this nice thing always happen in red. And then we multiply these together. But the rule for multiplication was explained before, the rotate and shrink. So you figure out what each one of these arrows is, and rotate and shrink. So this is nothing but a shrink. It always says when you have an interaction, shrink the amplitude by this factor, 0.098, whatever it is. I don't remember the number. Okay? I can remember the square upside down, but I can't remember the square root. So whenever a photon comes out or in, like this, and you draw this, that's where the C appears, the shrinking, each time you emit or absorb a photon. And the motion of electrons going from place to place is always governed by this, and the photon always by that. And by that way, in that way, you can figure out the amplitude for anything. because a whole world of electrons and photons, at least, is nothing but these three processes combined in various ways. That's all. As long as we don't talk about nuclear. Yes. That's all. It's done. The one point, however, if all I knew was that the electron started here and ended here and the photon ended here, this isn't the right amplitude. Why? And what would you do to do it right? Huh? What? Yes, you don't know where 4 was. This is the arrow if it happened to do it there. But it may have been that number 4 somewhere else. It might have been this point is here, or here, or here, or here. And for each of those points, there's a total amplitude. Those are alternative possibilities. Those amplitudes have to be summed. So we could say, we have to finish this for this particular problem by saying sum on all possible places, locations, and times that I've labeled 4. Sum this. Make this arrow for every place and add them all together.
How about the different colors of photons?
Different what? Nothing about colors of photons. Magic, there's no colors to photons. What colors the photons are will be explained shortly. You don't see it here. All other phenomena have to be explained in terms of this, and you can ask me one after the other, and I will do so. However, before I do so, I have to make sure you got the idea of the fundamental rules.
This position 4 then could be just anywhere.
Yes.
Is there, a way of now- is there a higher probability that it'll be at
You should be able to answer that now. You know very well, like when we're reflecting from a mirror, it can be anywhere. But in many places, a nearby place has the same amount, but it's at a different angle, and when you finished it up, it doesn't amount to much, so that there is some region that does the most. If these distances are very large, it's easy to find out where that is. If the distances are small, it's hard, the differences are not very great. It's like a small piece of mirror. So it's true that if these things are close together, reasonably close, and you put 4 over there, you get an arrow the same size, you get a pretty good arrow. But when you put the 4 not quite there, but here, you get a similar arrow of opposite directions or something, and all cancels out, or most of it's in the middle. Okay? Yes. Other question? Sir?
Why is the photon emitted at all?
Oh, I don't say why anything. I'm just telling you the rules. Oh, because I asked for the amplitude that we have an electron here, an electron there, and a photon here. I'm asking for that problem. So I have to find a photon. It's the only way I can get it.
Just assume it.
I'm asking a special problem. This is a special example in which I ask for a special simple problem. I started with an electron here, I find an electron there, and I find a photon going here. I'm going to do more complicated problems, right? That's a very simple one.
It's a radiation of a radio wave from a moving electron.
Yes.
Well, he means he puts a detector there for the photon, and he calculates the probability.
That's right. The square of this would be the probability, the square of this mess, would be the probability that if an electron were liberated here and were found later here, that you'd find a photon in the detector over there at that moment. All right? That's a special problem, and that's the answer to it, almost. I have to tell, there are always more diagrams, more pictures, more ways. Because this electron might have emitted a photon which was later absorbed by the same electron later, and all kinds of terrible things, which I now will explain. So let's take another problem. Well, this is a good one, but we'll leave it there, but we can take other ones to show how it's done. Suppose that I talk about what's usually called the scattering of 2 electrons. One starts at a certain moment from some place, and another starts from a moment from another place, and later you find them in 2 other places. And therefore we have an electron that may have got from here to here, and the other one may have got from here to here. Now let's calculate the amplitude for that. Let me call these positions 1, 2, 3, 4. And I'm going to make a few mistakes. I'm going to rush fast, and you're going to have a few mistakes we'll come back and fix. First of all, for this problem, and I'm drawing this line to save the other thing for the blackboard, for this problem the answer is simply E21, E12 times E34, right? Electron went from 1 to 2, electron went from 3 to 4. Okay? Anything else? Any remarks? Finish. No, not quite. Yes, a photon can go. Not from 1 to 4. But you could have a situation like this. This is the first picture. I haven't got room on the blackboard. I just love to keep this one. Well, let me erase this and make the picture smaller. So this first picture is now redrawn. Here's 1 and 2 and 3 and 4. Now this is now going to be the basis for the second picture. The second picture has a new possibility in it. That is that the electron went from 1 to 5 and emitted a photon, and the other electron went from 5 to 6 and picked it up. Yes, and what we're asking for now is the amplitude, a new problem, this part of this section, amplitude of electron originally at electrons at 1 and 2 go to 3 and 4. All right? What's wrong?
No, but isn't time going that way? You mean 1 and 3?
1 and 3 go to 2 and 4?
Yeah.
Of course. You're absolutely right. Electron 1 and 1 and 3 go respectively to 2 and 4. Okay? Now, this was the first term. That corresponds to this possibility. But this is also a possibility. And for this possibility, I'll write it down. I'm not going to write anymore because you'll see very quickly what that is. You're learning the principle. You're not going to actually calculate these. We don't know the formulas. But this would be things like E51. This was times, you remember, in the normal business of time. Times E25 times E63. How brainy do you have to be to write this down, huh? 46 times, wait a minute now, got to get a blue one. Yes, you do, yes, you do. Times P56 times, more? Yes, more. More? Yes, more. C times C. Anything else? Oh, yes. Sum. All places for 5 and for 6. Okay? Well, you get the principle now. It's, you have all these things happening. You multiply the amplitudes for all the things that are happening. What are those C's? Those are the junctions. For each junction, for each interaction, we have a factor C, or an amplitude C, a shrinker. And all of these are the amplitudes for the things to do what they have to do. Now, I have some questions for you. 1. What about the possibility that this photon simply comes out here instead of going over here and get absorbed? Why don't I add that in? Different event. Got it. We asked for a special event. We started with electrons at 1 and 3. We ended with electrons at 2 and 4 and nothing else. Something else is a different event. If I were asking for the question, we started with electrons at 1 and 3, and we want to have electrons at 2 and 4 and a photon at 17, that's a different problem, and we start all over again. Okay? You learned that because that was worrying you before. Right. Okay? I mean, in our conversations, the half-hour conversations, that was the thing that was bothering me. Are we finished? Is this the complete amplitude for this process? No. There are other possibilities that 2 photons go across and so on. And they write down very much more elaborate strings of these things. And adding this all together is a kind of a technical job of some complexity. So as the diagrams, and these are diagrams, they're called Feynman diagrams actually, as these diagrams become more complicated, they were invented by your speaker. As they become more complicated, each one, you see, each diagram represents a term in a sequence of terms. No, actually, they weren't. They get more complicated and there's more calculation needed to compute them. So how can we make any calculations? We got the whole string. We're saved in electricity by the fact that this C is small. And the more C's you have, the more shrinkings you do, each by a tenth. And the contributions, there's two of them here. This is 100th the size of that, roughly speaking. And then 100th again, and 100th again. So if we wanted to calculate the 1 part in 10 to the 8th, we'd just go laboriously to the 10th order diagram. 4th order. Four extra photons going across, okay?
What does that mean about the C shrinking more and more?
The C is a shrinker, right? It shrinks by a factor of 10. I have here 2 C's. So in this amplitude, I have shrunk it twice by a tenth, so it's not very big. In the next one, if I had 2 photons, I'd have 4 C's. Each one is a shrink, and they go shrink, 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 shrink. I can hardly see it, and so on. Okay, that's what I meant. Yes.
Okay, within the realm of those where you don't have too many C's building up.
Yes.
How about where the electron goes in a straight line and the photon leaves it and comes back?
Yes, it's possible. There are all kinds of new possibilities. I'll draw a few. I think we would be done with this. All kinds of things can happen, frighteningly amazing things. And all have to be included. And many of them have interesting physical effects. I will not go into the very many details, but show you a few of them. For example, one kind of a thing that could happen, I'm not going to draw all the things that can happen, but a few, was that we had this photon that we wanted to go across that was analogous to that, but another photon left this one and didn't go across here. That's all right, that's easy, we understood that one. But surprise, it leaves this and comes back to the same electron. An electron interacting with itself, so to speak. It spits out a photon and says, wait a minute, come back, please. Okay? And so the spit is a shrinking amplitude, and the re-sucking in is another one. This is a one of order C4. C4, 4 C's. That can happen. And may I tell you something else that can happen? Well, now we might notice something interesting. Remark. Either 6 is later than 5 or it's earlier. Yeah, I think that's all right. If 6 is later than 5, we probably say that the photon left 5 and go to 6, because we like causality. If 6 is earlier than 5, we'd say the photon left 6 and went to 5. It's not important to worry about which. It's just an accident of the tail. We're summing over all possibilities. And what this formula doesn't do anything special when you change the order, if you looked at it. And so it's just where T5 minus T6 is 0. It doesn't do anything special. So we don't bother to be careful to say which one emitted and which one absorbed and which way the photon is going. We just say it's exchanged a photon, because to be too careful about which way, we would have to think of this diagram twice. Once when it was from one to the other and once vice versa, but they're both part of the same disease. Okay? Now in this kind of a diagram, and let me take a simpler one so I don't frighten you with 2 things at once. Let's take the one in which I exchange 2 photons. Let's say, for instance, this way. In that case, there are 2 C's, of course. There's another way it could happen. When I'm moving all these points, 5, 6, and 7, and 8, they would have labels, and there would be a big formula, and I'm not going to write it down. 5, 6, well, this was 5 and 6 before, so let's keep that looking like that. You can't tell which is which, actually. 7 and 8, and they would all be moving around. There would be a circumstance of positioning in which 8 is earlier than 6. And therefore, we'd have a situation which would look something like this if we had that happen. It would look like this. There's this, then that. And then on this one, we'd have a section in which 8 is earlier than 6. So that would mean we go up to 6 and come back to 8 and go forwards again. Huh? Go up, 8 is here and 6 is here. This is 7 and 5. And the photons corresponding are connected together. This is not a new diagram. This is part of what you have when you add this for all positions 5 and 6 and 8 and 7. That add in automatically, right? Why is this curious? Because in this one we're saying that an electron goes up to here in time, then backs away in time to this point, and then goes forward again. This would imply that sometimes electrons can be found going backwards in time. Nothing to stop it, only interferences. And sometimes it's possible to arrange things so that the interferences make it true that this contribution of the backward section is in fact a very large one. And this becomes a real thing, an electron going backwards in time. And if you find out what in physics it corresponds to, it turns out to correspond to a new particle called a positron. It's the opposite. Electron going backwards in time behaves like an electron of the opposite charge, a particle of opposite charge. Such a particle was discovered. It's called a positron. Photons can make electrons and positrons in pair. It was an experiment. Or when an electron meets a positron, they annihilate completely and produce just a pair of photons, for instance, by this process. Here's an electron going forward, here's an electron going backward. Huh? It's part of some other more complicated diagram, perhaps. And 2 photons are emitted. That's a typical example of a very nice process. And happens in the laboratory. You have a positron and an electron come together and disappear. Another way to understand this wonderful thing is to look at this diagram more completely and see what it could possibly mean. The way to do it is this. Time is going this way. So we can see what we have in the world by taking a slice of time. Forget about the photons for a moment. And never mind this electron. Just let's look at this part, because that's the curious part. There we have 1 electron, 1 electron, 1 electron, 1 electron, 3 things. All of a sudden, from somewhere, 2 new ones are formed. And then it goes along, and 2 of them disappear. We have found in a laboratory just such processes. By using photons, we can make them collide and produce a pair, an electron and a positron, 2 new particles. Or we can find an electron and a positron that come together and disappear. In creating them or in disappearing, they always have to be interacting somehow with a photon, or at least one. There has to be a junction point here. This is an example of an annihilation into 2 photons. If I turn the diagram upside down that way, it would be 2 photons coming together to make an electron and a positron. If I turn this diagram on its side, it would look like this.
Can that event go outside of the laboratory?
Just a moment. They all do. This one and this one do. Yes. This is called the scattering of light. An electron absorbs a photon and it's lost, and then it emits a new photon and comes out. As you can well guess, the formula for this and this are very closely related. They involve 3 E's, 2 P's, 2 C's, and so on. They're very closely related. And the formulas for a pair annihilation into photon pair and the formula for what's called the Compton effect, or the scattering of photons by an electron, are very closely related. You just change a couple of signs in them and boom, you've got the other formula. Well, that's very curious because it's a new phenomenon that quantum mechanics and relativity together predict. And actually, it was discovered before the full... No, it was predicted by Dirac that there would be a new particle, a positron, before it was discovered by a few years. And it was discovered. And it does all the right things. And all the formulas for properties of positrons are already in our formulas for electrons. So that was a happy discovery. Okay?
Why you didn't say happy coincidence?
No, no. Well, if it didn't work, we would have to be telling you about a different theory today. Yes?
Back to the first order term where you have 2 electron
Yes.
lines, and the photon just comes out and goes back into the same electron.
Oh, that could happen too, yes.
Do you have a separate amplitude for it being in that, on that electron path as compared to the other electron path?
No, you have to add them together. You don't know which one it happens. You have to add everything. If you add this, plus what he's talking about is a picture that would look like this. Plus a picture in which this would be over here, plus a picture in which on both, plus there's a picture on where they're on both, but there's another one going across, plus, plus, plus. Gee, this is a terrible thing to calculate. But every one of them gets smaller because of the C's. But in a given order, that is a certain number of C's, the number of different style diagrams, the type diagrams is limited. But it grows very rapidly as you add more C's. And there are guys in the halls of Caltech that are sweating with the 2,800 diagrams that they're trying to calculate for the 6th order term for something. How can a human being do that? He can't. So they made computers who make the diagrams according to the rules, count how many there are, and for each type essentially writes this down, but knows the formulas for all this and simply calculates, adds all the stuff together, and tells you the amplitude at the end.
10 years later.
Not really. The computers are really quite fast. It goes like this. It's done in a few days, after you've got the formulas right, after you get the bugs out. Bugs are the hard part in computers. Then it's done in a few days by somebody. But then somebody, for a thesis, thinks it's important because the measurements are getting more accurate to do the next order. So he has 35,000 diagrams, right? And he just makes the computer up to its edge. We always work at the edge. And so indeed it takes a few weeks. It always takes a few weeks because it's the newest computer with the greatest speed, but it's the hardest problem we've done so far. So we're always in the same, always taking a long time.
What would the hydrogen atom look like? The electron bond?
I can't tell you because I haven't put in the proton.
Or would it be just a positive?
I'll tell you in a minute, but I haven't put the proton in. I have to tell you what to do about a proton. So I'll tell you in a few minutes or tomorrow.
Where does antimatter fit in?
That's antimatter, an anti-electron.
That's it.
That's an example of antimatter. If electron is called matter, then antimatter is an electron going backwards in time. Yes.
And all the other antimatters are the same thing.
Yes, and it turns out that this is a general principle because I told you that every particle we call this a propagator sometimes. The thing that goes for amplitude from one point to the other. Every particle propagates by the same function but with different mass numbers in. And that function isn't zero when you reverse the order. Every particle has an antiparticle. Say, what about a photon? Every particle has an antiparticle, but some of them, the antiparticle is the same as the particle. The photon is an example. We don't call it a different particle when it goes the other way. It looks the same, does the same thing, so it's an accident. I would like to say every particle has an antiparticle, but some of them don't look like they have, a few of them. Photon is an example. But the electron, this section of tubing behaves different than the other section, and you can tell the difference. It's got a different charge. So that's an example of antimatter. This is getting to be a wonderful... I must have some kind of a thing that I turn. It's like when you waltz. After a while, the girl asks you to go the other way, please. Yes.
What order in orders of C are playing around with diagrams these days on the computer?
Today, orders of C of the order are more or less, well, let's say, sometimes a particular process can't be done at all unless you have, say, a photon exchange or something. It just doesn't happen. Those are very easy. They're the lowest order you compute in no time. Then we calculate corrections. And really what you want to know is how many extra orders of C do we do? And generally, where it's hard, something like 4 orders of C squared, 8 orders of C is about the limit at the present time. Most of the calculations are 6 orders. I had to say where it's hard. There are special places where you can calculate hundreds and hundreds of orders, approximately. And one of them is the hydrogen atom, which I will now describe. Okay. I think that almost all, before I go to the hydrogen atom, I have to tell you about one other thing. In spite of the attention of my students here, you've missed something. You didn't ask me something which is here, an obvious problem. You may have thought of it, and I was talking too fast. I shall hope so. All I know is that I had an electron at 1 and 3, and I end up with 1 and 2 and 4. What about this diagram, that this one starts at 1, and it comes to the one that goes here, and this one goes here? Good. Congratulations.
Except for the grams, but you don't know the difference.
There's no way to tell because electrons are identical. Okay? So they interfere by adding the amplitude for the two cases.
Surely you were leaving that out on purpose.
No. No. Now, it turns out, yes, that I left out something, which is the polarization of electrons. And the polarization of electrons means that electrons come in two different kinds that are related to space, just like photons are polarized X and Y. A thing I've left out is a complication. When I put that in, the most amazing thing happens. And that is that if you see an electron and has a certain amplitude for being there, if you looked away and I turned that electron around 360 degrees, the amplitude changes sign. That is absolutely nutty. I mean, it's the same situation. So how do you know whether an electron's been twisted around or not? Well, you notice when I did that trick on some exercise that we were doing, that when I turned 360 degrees, I was wrapped up, and it means something, and you can define that. But 720 degrees would not be. 720 degrees is two 360s. I changed the sign twice. I really am back where I was before. But the polarization rules for the electron, which is called spin-a-half particle, are such that when you rotate 360 degrees, the amplitudes change sign. It isn't at all obvious. In fact, it's not known to most people, and as a matter of fact, it may not be true. But I suspect that the problem is that when you exchange them, have you inadvertently turned one around? And that's a very delicate problem, because you can't define whether it's the same electron or it corresponds to the electron turned around 360 degrees. At any rate, in practice, when you deal with the polarization, the exchange one is of opposite sign. It's as though when you change them, it's the same thing as turning one around. It has the same effect. It changes the sign. So in practice, actually, because of the polarization of electrons, this diagram contributes negative of what you would have thought to this, and these cancel. These are opposite in sign. When we have to, in order to make the rule then for electrons and to disregard this fact about polarization, just to say, all right, I'm going to believe that I'm including that, then the rule is that if the diagram corresponds to exchanging the identity of a pair of electrons, then when you superpose them, you subtract rather than adding, or you change the sign of the exchanged one. That looks like an odd gimmick, an extra piece, and it's true, it's concerned many people to try to explain it. I believe I have given you the clue to the explanation, but it hasn't been thoroughly analyzed. We just know the rule. Okay? We know why it has to be, and there's various arguments that if it were the other way, you would get sums of probabilities wouldn't add up to 100% and all kinds of other difficulties. So we're sure that it's right, but it is true. So the arrow that you get for this one has to be reversed before you add it to that one. It's a special rule. It's called the Pauli exclusion principle, or the Pauli exchange principle. When you exchange a pair of electrons in an analysis, you must remember that the amplitude for that case, when you exchange the identities, you thought this pair went here. No, maybe they went there. You subtract that second case. Let me show you something. That means that two electrons can't come to the same point. Two electrons can't get to the same condition. Because suppose that these 2 points were very close together. These 2 points are very close together, 2 and 4. And I come from distant 1 and 3. Then I have to add the amplitude for this one to the amplitude for this, but I'm supposed to subtract, right? What are these amplitudes? This one was E12 times E34. This one is E14 times E23. And the answer is that. Subtract. Now, if 2 and 4 are the same, or nearly the same, this E12 is almost the same as E14. The amplitude to go from this to 2 is almost the same as to go from here to 4. So this is almost exactly the same as this, and this is almost exactly the same as that, and therefore nothing is left. And so the amplitude the two electrons arrive nearly at the same place is 0. That turns into the rule for atoms that no two electrons can be in the same character of motion, or as a state or orbital motion in the same state inside the atom, and it's due to the same rule. It's the exclusion principle that keeps electrons from being too close together or doing the same thing. Okay?
How was that originally worked out?
It was discovered backwards. After the... no, it was discovered backwards. Atoms were known in their levels and properties. And when the quantum mechanics was invented and they tried to fit the levels, they find many particular patterns of motion missing. And at first the rule was that only two electrons can be in the same state. Then later it was discovered that the electron has a polarization, spin. And it turns out it means that they can't be in the same motion and spin. So no two electrons can be in the same complete state. At the same time, it was realized by Pauli when he looked at Schrödinger's equation to find out. He made that rule when they didn't have the full quantum mechanics, we just had Bohr orbits and so on. But the full quantum mechanical equation of Schrödinger, you could solve the equation, say, for helium, which has two electrons, and get a lot of levels which didn't exist. But all the ones that didn't exist were amplitudes in which if you exchanged the pair, it wouldn't change sign. Only the ones that when you exchange a pair changed sign were the levels which existed. And so he realized that that was the correct statement of his previous so-called exclusion principle. Historically, that's how it was found. Of course, he was the one who found the second thing as well as the first because he was so interested in it. He had discovered the first rule and it was mysterious, and when the new quantum mechanics came out, it turned into this rule, which still has some air of mystery about it. But I believe it's nothing but it's definitely related to the fact that inadvertently you've turned something 360 degrees when you've exchanged it. But I don't want to explain why I think that in great detail, all right?
Would you repeat the first rule you say with the replacement?
What?
Would you repeat something you already said? What was the first rule that Pauli came up with?
It was a rule, when they had, was an early rule in which there was some kind of a theory that there were special orbits that the electrons could go around in, and those were fixed orbits. It was pre-modern quantum theory. It was a half-assed between classical and quantum. So they had orbits with sort of tracks. You could either be in this orbit or that orbit. All these atom drawings that you see on pictures where they have these nice little circle orbits, those are from those days, okay? There were only certain orbits allowed. And he noticed that he would understand the entire periodic table, how the various chemical elements come and so on, because various orbits got filled up, he said. You can't put more than one electron in more than two electrons in any given orbit. So he had this Aufbau principle, atom construction principle, that any orbit can only hold at most two electrons. And then we have a third electron has to go to a higher orbit of lower energy and so on. This makes all kinds of very interesting variations in the properties of atoms, depending on whether they're 2, 3, 4, and so on electrons. 2, 3, 4, and so on electrons are helium, lithium, boron, and so all these chemical differences, this wonderful variety, all comes from this rule. And it's glorious. You understand the whole periodic table from this rule, the chemicals.
Yeah, if we
And
this, everything
just-
would collapse into proton, everything would collapse.
I'll tell you in just a second. Just let me finish the little sentences, okay? Which I can't remember now. But, well, yes. Then after that orbit theory came the real quantum mechanics, and he had to translate what that meant in the new language. And it turns out it means that states in which when you exchange the coordinates of the two electrons, only states with when you change the coordinates around change sign, the amplitude you change sign. All right, see if I change 2 and 4 in here and in here, I just reverse this for that and change the sign of the answer. So the general rule is if you exchange a pair of electrons, you have to change the sign of the contribution. And that's the statement of the exclusion principle in the more modern form. If the exclusion principle weren't right, then if you started with an atom with one electron going around the nucleus, you had a heavier nucleus, you put 2 electrons in that orbit, a heavier one, 3, and so on. Then the various nuclei, 1, 2, 3, 4, which would be what our hydrogen nucleus, the helium nucleus, lithium nucleus, beryllium nucleus, boron nucleus, and so on, 1, 2, 3, 4, 5. And we just have 1, 2, 3, 4, 5 electrons, all tighter and tighter into the orbit. All the elements would be very similar. There would be a kind of smooth scale between them. A particular element in the periodic table would be very close in its properties to the average of one on each side. But that's not at all the way chemicals look. Each substance seems to be quite independent, so that the chemists have something to do, studying and learning the valence of vanadium, and then chromium and manganese, and they're all different kinds of things. And because of this filling of orbits, it goes into new orbits and new variety of new properties and so forth. Yes?
Is the polarization index of the electron somehow hidden in this fact?
I haven't said a word about polarization. My formulas are all wrong. I imagine there's only one kind of polarization for the electron. This is the amplitude that goes from here to here. Actually, there are 4 amplitudes. An electron can appear in one of 2 kinds of polarizations. And I have to say, what is the amplitude of an electron in this polarization, goes to here and appears to be in the same polarization, or the opposite polarization? Or, if it starts in the opposite polarization, what's it for the other one, 2, 4, right? So there are 4 functions here. And they're a little more complicated, okay? Likewise for this, there are more functions. It's more complicated than I said, but not fundamentally, okay? The one place where the complication is really relatively, you might say I was cheating if you knew the formula. Somebody who's an expert sitting here would say he's cheating. I've only got one amplitude for the interaction, one number, shrink. That shrink is right. But actually there's quite a large number, because there's an amplitude that an electron spinning this way emits a photon polarized that way and ends up with the electron coming out spinning that. Excuse me, I said spinning, but there are 2 polarization states. They're called spin up and spin down. And the polarization of the photon is called polarization X and polarization Y. So we have an amplitude that an up-spinning electron emits a photon at polarized X and appears after the event, starting out from that point, as a down-spinning electron. Or, and if you think about it, there are 12, 4, 3, 8 numbers or something. There's a lot of numbers for the different cases. All the numbers, however, which are complex numbers, are simply ruled like 0. It doesn't happen. Or, it happens, but you must turn the arrow 90 degrees for that. Or, you must turn the arrow back 90 degrees for that. They're just very simple rules, just a list of them, huh? Except each one always has the shrink in it. So I simplified all that to get the idea how everything works. But since we're not actually calculating, we haven't got that complication, and I am cheating.
Okay, what I was really concerned about was your statement of the exclusion principle applies to similar type of electrons.
Anything that's polarized, like electrons are polarized, does the same thing. Yeah, and the key of that the very strange character of the polarization is that if you take a system, take the electron, look at it and again in different cases, and it corresponds to turning your viewpoint around by 360 degrees, which you would think would have no effect at all, changes the sign of the amplitude. And so you can remember this rule by saying, when you exchange, you inadvertently have turned one 360 degrees, whatever that means, and for whatever reason. I can supply the reason, but it would lead me a partial explanation of the reason, but it would lead me too far astray.
What about the case of circular polarization?
That's light. That corresponds to this, that there's an equal amplitude for finding X as there is for Y, except they're equal, but they're 90 degrees out. That means they're right angles. The arrows are at right angles. You see, you have to have 2 arrows for a photon now. The amplitude to find it X polarized, that's a certain arrow. The amplitude to find it Y polarized, that's a different arrow. If you have light which is circularly polarized, that corresponds to the case where the arrows are of the same size and are at right angles. If you have purely X polarized light, it means that the Y amplitude is 0. There are 2 arrows always for a photon, not just one, which are answering 2 different questions. What is the amplitude that it comes out as an X polarized, and what is the amplitude that comes out Y polarized? You might ask for other combinations, what is the amplitude that comes out that they're at right angles, and all kinds of other questions, and that's asking about what you call circular polarization and so on. I don't want to discuss polarization more. All I want to do is discuss it far enough to tell you that it isn't changing the principles which I'm trying to explain. We don't want to know too much detail. We're not going to calculate anyway. All right? It is a little more complicated. A second point to make, though, is that the mathematical structures of these numbers and polarizations and so on are not like this empirical mystery of .08987. They are deep in the theory of geometry and quantum mechanics. The numbers for the polarizations and the possibilities are easy to deduce by purely mathematical reasoning. This number is not. It's a completely unknown number. But these 90 degrees and this and that this is turned and that's turned, and what the various numbers are for the different combinations and how they have to be is determined by a kind of deep logic about geometry, plus some principles that the amplitudes must always add up to 100% for all past cases, and some other principles. That the answer shouldn't depend on what coordinates, where you put those axes for the walls, for instance. And when you add all those things together, we can deduce all these relative numbers for the different polarization cases as rather beautiful mathematical things. And that's one of the places where that make me say, and I've said in many places and many people have remarked, in fact some of you came up to me especially and said, do you really mean this? That you cannot fully understand the beauty of nature without understanding mathematics, at least today. Because the fact that all those numbers can be deduced is gorgeous. The fact that this function can only be one function, the same one all the time, and the only thing we have in it is the scale, is also deducible. It isn't just empirical. It's deducible from logical things about assumptions about the uniformity of space and time. The fact that energy is conserved in the world is simply a result of the principles of quantum mechanics about amplitudes, and one more statement, that it shouldn't make any difference at what time you do an experiment. That if you did an experiment on a particular moment, and for a certain interval, and then you did the same experiment an hour later with new apparatus, it doesn't make any difference. Or the statement that the amplitude shouldn't depend, that means the amplitude for a given problem shouldn't depend on the absolute time at which you're making the calculation. That statement alone is enough to prove the conservation of energy. I wish I had enough time, I could do that. Actually, that's a nice derivation. And same thing, if you suppose that you're calculating an amplitude for this to go to here, and you get a number, if you'll only suppose that space is homogeneous, meaning if I computed the same problem for the amplitude to go from here to here to here to here, moved over to the left, I should get the same amplitude. Once I say that, I can prove the theorem of conservation of momentum in that direction. If I say that it doesn't make any difference in what direction axes I choose, whether I take my apparatus, compute it this way, or I take the apparatus and compute it that way, I turned it. If you say the answers mustn't depend upon that, then you can deduce the conservation laws of angular momentum and more. The nature of angular momentum in quantum mechanics is closely related to this polarization question, which I talked about. The polarization and the angular momentum are really two different things. The fact that an electron can have only angular momentum of a half a unit is all deducible by sheer reasoning from the simple principles that the answer shouldn't depend, the amplitudes, the probabilities shouldn't depend on the axes. You see, the new thing that's possible is that the amplitude, the arrow does depend on the orientation, but the length doesn't. That's a new mathematical possibility that isn't in an old-fashioned world. There, it's simple. In the classical world, you just turn it, it looks exactly the same, there's no change. But now we're allowing a change. That when you turn it, the amplitudes do change, but the lengths don't change. And that new possibility makes all kinds of marvelous new mathematical things. And it's really quite beautiful. And I can't resist saying, therefore, that one cannot really feel the glory of nature without a good understanding of mathematics. Okay?
Amen.
Well, it's 10 minutes to, and let me think if there's any little point I want to make now. Yes, the nucleus. Let's just talk about the nucleus for 10 minutes. Did you say I left something else?
Sentence about photon color.
Yes, we're going to have to do that next time.
Okay.
There was the question about the nucleus. And what I would just say is in a nucleus, at the level at which I want to calculate here, I put a line here, because these are fundamental and they're still correct today. What's below this line is an approximation for which we have a much more detailed understanding and a much more accurate way of saying it. This is an approximation and therefore should be made in purple, of course. Approximations are always in purple. And that is that the nucleus, yes, nucleus, such and such, each nucleus has an amplitude to go from one point to another, which is f of 1 and 2, and m, where this number depends on the nucleus. And each nucleus interacts with photons. I'm not talking about gamma rays, that excite the nucleus, but the dullest nucleus, where they're not excited, like inside a hydrogen atom, the nucleus doesn't get excited, or a helium atom. And in those circumstances, at the lowest level, this is not a complete statement. It interacts through C with a photon times a multiple of C, an integral multiple of C that depends on the nucleus. Z times C. Z is an integer, 1, 2, 3, 4, 5. A nucleus is therefore, each different nucleus has different values of M and different values of Z. I don't mean every nucleus is different in Z, and there may be two nuclei which have the same Z but different M. Those are called isotopes. Z determines the chemical properties. It's called the atomic number of that nucleus.
How many numbers of electrons there are normally?
Normally, yes, it is equal. As you show from the interaction, it gets neutralized when there are a lot of Z electrons around that nucleus. So a neutral atom has Z electrons around this nucleus. But that's a consequence of this rule. Yes. So this is enough to take care of the duller aspects of chemistry and so forth, nuclei, not the dramatic stuff like atomic transformations, radioactivity, and so on are not included. To do that, I have to dig in and tell you that what's happening in a nucleus is lots of little things going around too, and describe it some other way. This is therefore only an approximation. With that, I can explain what a hydrogen atom is. The M's, by the way, for nuclei are much bigger than they are for electrons. And there's a table of them somewhere. There are hundreds of these nuclei. There's only one of these and one of these. You know, I've already had hundreds of things. Not satisfactory, but we have a theory for that. We would draw a picture, well, since the nucleus was approximate, we'll put it in purple. This represents a nucleus. I draw it as the sign of a heavy one instead of a simple line. And then we have a black line for electron. And blue lines for photons. And the electron exchanges with the nucleus by exchanging a photon. And it goes. Now, I've drawn them as if they never cross. I haven't drawn you one like this, because this is much smaller. It turns out, because of the smallness of C and some other things, that the time between this and this is usually so great that it's not much amplitude to cross. They cancel out, almost. But they should be put in to get it very accurate. But an approximation like this, where they don't cross, there's a C here and a ZC here, a C here and a ZC here, and so on. And so on. And that's what an atom looks like, a situation where you're adding all kinds of terms like that, with various numbers of photons exchanged and so on, to find out this is an amplitude that a nucleus here with an electron here ends up as a nucleus there with an electron there. The photons are never seen. That's a normal state of an atom. Of course, it could happen. And we have another problem. We do a different problem. Maybe we have a photon here at the end. Light might have come out from in here. This represents a situation where an excited atom emits a photon and goes into a new condition. But an atom has to be analyzed by very, very large numbers of these terms, and that's done by a method called differential equations to solve what the behavior will be, but I don't want to explain the clever way in which we've been able to solve what happens if we sum enormous numbers of these. Okay? It doesn't help you much, but that's what we would have to do a nucleus. And if we had enough mathematical technique, I can show you how it all works. Are there any other questions? It is true, I left something out that you mentioned just to me, just before we mentioned this.
Photon color.
The what?
Photon color.
Photon color. Yes, what I must do there is to go back over the double slit, the film and so forth, and tell you from this point of view how that works. It would be an appropriate thing to do right now, but it's 2 hours now and we should stop. I'll explain the color.
In working with these diagrams, as a property of a photon.
No, there's no, you don't have anything to do with the colors. This is the amplitude that a photon goes from one place to the other. And there it is right here. We've done the photon correctly.
And so you don't have to like assemble the possibly different colors of that photon.
No, you've already done it. I will explain the color. You see, I have to remind you that in order to make a colored photon, we have to have a pretty big apparatus, a special way of emitting a photon. And we have to look at what did we do to make that happen. What it really corresponds to, and I'll tell you, is that the amplitude of a photon arrive here, or to arrive here, or to arrive here at the same place at different times varies with time in a nice, just by rotating. That takes a very special piece of apparatus, a special kind of source, so that the amplitude that the photon arrives here, 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 they only differ by turning at a certain rate. That rate determines the color, and this is a monochromatic source. That's really your answer, okay? That the amplitude of the photon arrives at a particular point in space varies with time simply by turning and in no other way. That's a monochromatic source, a special problem, all right? That's the answer to it, really, and I'll do it in more detail next time. Okay? Yes.
If you have a free electron in space and you have a photon losing out energy back in again,
Yes.
and you have lots and lots of energy, that contributes energy to the
No, energy is all contained in here. You have no other things to consider. There's nothing else but this in physics.
so it's self-energy. I mean, there's no way the self-energy relates to all
Yes, it does.
photons coming in and out.
Yes, it does. Well, you know about the infinities and all that stuff. I haven't got time to deal with that here. If I had 2 more lectures or something like that instead of 1 more, I could tell you where we stand and where all those infinities are and what you do with them and so on, but I can't do that. I have some other things that I have to do. One is it behooves me, since I brought up this other way of making analysis in the beginning for that slit thing, to tell you the deeper way of looking at that slit. That's important. It's also fairly important that I give you at least one example of the kind of a thing that can give those 3/4 in those boxes. That's going to take the next 2 hours. I can't do any more. All right?
Great.
So that's as far as I'm going to be able to go.
What about magnetic moments and things like that?
That's as far as I'm going to be able to go. That has to do with the special values of these E's and so on for different kinds of polarization. Whether the spin is up or down, the effects of the photons are slightly different. These differences we call the magnetic effects of up and down spinning objects and so on. It's all there, actually,
So you got
hidden.
magnetic moments and
Yes, they're in the... Oh, excuse me, no, I left that out, the proton. My nuclei was supposed to be so simple I wasn't worrying about that. If you had that, you have to add some more corrections for the nature of the interaction. It's dirty. You do a lot of dirty stuff with the nuclei to do more and more accurate as you study more and more properties. I wasn't worrying about the magnetic moments. I made a mistake. It's also true that many nuclei are sort of oblate, and they don't act like little point charges, which is what I assumed. The interaction is slightly more complicated. That has to be put in too. These complications are really the result of the fact that nucleus isn't simple, and it's being approximated. There's no such complications here.
nuclear magnetic resonance gets complicated.
It revolves more detailed properties of the nucleus than I made believe were right here. It's not, this isn't quite detailed enough to deal with that. Yes. Time's up.
Thank you.
Okay, yes, thank you.